Good morning, everyone. My name is Chandler Carruth. I'm here with my colleagues Josh and Richard, all of us working on the Carbon project. And we're here to talk about DefinitionChecked Generics. I'm going to start off, but we'll be passing the microphone as we go through. And just as a reminder, this is going to be a two-part talk. So I hope you all are ready and pumped for a long and exciting adventure around generic code. All right, with that, I'm going to get started. So let's talk about DefinitionChecked Generics, both the why and the how. Although in the first part, I want to start really focusing a little bit on the why of checked generics. First off, we should at least just make sure we agree on what checked generics are. Right? This is fully type checking the generic definition of some generic piece of code. Okay. Another way of thinking about this is it's a finite set of constraints on a generic parameters that are both necessary and sufficient to guarantee successful instantiation, right? And definition checking is something that was really exciting when people were first talking about concepts, and I don't mean concepts that came into C++20, but I mean the concepts that started before C++11. There was a lot of effort around C++OX concepts, and one of the things it was trying to achieve was definition checking. When C++20 concepts came out, one of the big question marks was, would we be able to actually definition check them? Is it possible for C++20's constrained templates and concepts to be definition checked? And so rather than diving into definition checking and all the motivations, I thought let's start with a nice kind of puzzle that's all like C++ that you all know and you can actually go and compile and see how it works. Let's start with what we actually have today. Let's start with C++20 constrained templates. All right, and these are fundamentally based around assertions of expression validity, right? The concept lists a set of expressions that as given must be valid, okay? Or you can't actually use that type parameter to a particular template. But it doesn't specify their semantics when valid. We still rely on instantiation to get the semantic meaning. And that's where we typically fully type check. But it's kind of an interesting thought experiment to say like, well, could we definition check with these? Because I think it's, maybe we're done. Maybe we already have this. And the rest of this talk can just be kind of partying about all the cool stuff we can do. All right, so let's start with something easy. Okay, we have a nice little display concept here. It's going to have one expression that we require to be valid, right? This d.show, we have to be able to call a method show on D. We have to be able to pass it a string view argument. That has to be valid, all right? We look down here, in fact, the template that we're using it with, we call show and we pass it a string view argument. This is definitely valid. We could fully definition check this, right? The constraints here are both necessary and sufficient to guarantee that this instantiates, right? Unfortunately, the code usually isn't quite this simple inside of templates. We might have some other codes. We might have something which is going to have a string in here, this name string, and it's going to add it to a couple of other pieces to say hello world. And that's going to produce a temporary stood string. Right, but this should still be okay because d.show with a string view, right? If you can pass a string view to d.show, well, stood string implicitly converts to string view. And so this almost seems like it's okay until you get the delightful other input to this. So my display here is a type which satisfies the concept check. We can pass a string view to d.show. No problem at all. But we can't instantiate the template. All right, if you put this code into Compiler Explorer, like it produces a very beautiful error message explaining that, in fact, you can't do this because we have an implicit conversion up here. You need another implicit conversion through formatted text. That's not going to work, and everything goes downhill from there. All right, so when we're actually specifying this, because we just said that d.show with an actual string view was valid, we didn't say anything about which implicit conversions would be available. Like maybe it just works by chance, but we didn't say anything that would actually be sufficient for us to understand. Okay, so this isn't the definition check yet, but we can fix this, right? All right, so what we're going to do is we're going to create a converts to template that just kind of models something that converts to a T. And we can add another expression that has to be valid, right? We can say that like you also have to be able to pass something that converts to string view, right? And if you do this, then this concept will like correctly reject the formatted text thing because it wouldn't instantiate anyways. So we're getting pretty close here. But if you try to use this, this doesn't work super well either. Because what happens if you pass, oh sorry, we also have to have the original one, because otherwise you'd be able to pass every type except string view to this. And that'd be kind of awkward. But this is still pretty awkward. Because what happens if you pass an R value to d.show, right? We actually need to make sure that we can pass an R value to d.show and that doesn't do something completely different. Maybe it's actually got some qualifiers or it's a deleted function in there. And not just an R value, we also need to have a const string view, because you might have a const string view instead of a non-const one. And then you might have a const R value string view. We can probably keep going here for a while. It's just starting to get a little bit kind of tedious as we keep basically walking through every single step of the C++ type checker and adding another constraint. And we're actually far from done. It gets much worse than this. What if you imagine you have some slightly more complicated code, okay? And in this complicated code, we have a little bit more fancy stuff, and let's see what actually ends up happening here. So we have a custom version of show that accepts a std string. Okay, but like the expression's still going to be valid. Like we can still call that with a std string. There's no instantiation problem yet, okay? But that separate version has a different return type. It returns an int instead of a double. But I mean, that's okay. And we're using it as a parameter to a function that does have an int overload. And so okay, this will still instantiate. We haven't exploded yet. And I mean, all this, like, we're going to select a different overload, so that's going to have a different return type int, and that's going to impact the return, the type of time. But that's just, okay, so the variable has a different type. This still instantiates. But eventually we're going to get down to record time, and we're going to try and pass an int to record time, which expects a double reference. And that's not going to work very well, and so we'll get an error. But this bad display passes our concept check. Right? And think about how many steps you're going to have to replicate in the concept in order to detect that this bad display is wrong. Right? We have to step through the return type of show. Then we have to step through the return type of scale time based on which overload is selected. And then we have to go into the variable. Like, we're going to basically reproduce the entire type checking of the body of the function in the constraint as a series of weird expression validity things. So my argument is that definition checking in C++20 concepts, it's not impossible in a kind of theoretical mathematical sense. It is conceivable to imagine a system where you produce the entire set of expressions, basically this fully, a set of expressions that fully subsumes the type checking of the definition in every concept, and that your implementation requires that, and at any point where there is any possibility of deviation, it says, no, you actually need to add more constraints to your concept in order for this to be definition checked. But that seems really infeasible to work with, right? We're going to build this observational record of how the type checker, and at that point, we've basically built another mini type system inside of the concept constraints. Except instead of a direct type system that we're used to working with, it's this weird indirect type system that is merely implied by an ever-growing set of equations that must always be true. And that doesn't sound like a great way to write code. This gets my brownie face. And so this is why I think that, like, while maybe in a very theoretical sense, C++20 concepts don't preclude definition checking, in practice they do. And that's why we don't have definition checking, and why I want to try and motivate folks to actually pursue definition checking in C++ and any other language. I think it's really important. So to talk a little bit about that, why is checking your generic definitions useful? Like, why is it so important? And I just do want to say, like, it's a little odd giving this section of this talk to this audience, because I think 50 or 80% of all of what I have here is stuff I learned from people at this conference. So I feel like the advocates here have done an excellent job. So the reason that at least I thought we wanted checked generics, the kind of initial reason, was because of better error messages. And if folks aren't familiar, C++ template error messages are awful. People complain about them a lot. But it's not clear that we need all of concepts for this. For example, we need definition checking for this. There's an example from the original concepts light paper, which is what led to C++20 concepts and doesn't really provide definition checking, about the kind of errors that they expect to get. And these are actually pretty good. Now, if you go and you put this code into your favorite compiler, I suspect you won't get a good error message right now. And I say that because I wanted to do that and show how awesome the error messages were. But apparently, our standard libraries aren't using concepts really heavily yet. And so they actually give me template error messages. And so a slight request for the compiler vendors and the standard library vendors to get some more concepts into their STL. But we can build pretty good error messages here. And we know that there's actually a paper, P2429, that really walks through where error messages are struggling in C++, right? The tweet that I use as a complaint is actually from this paper. There's a really thorough analysis, and it points out how you do need C++20 concepts. You do need something, but that looks sufficient. That what people are really needing here is some way of explaining, what is a failed constraint. And C++20 concepts are probably enough for that. But there's another aspect of error messages. And there are also lots of other aspects of error messages that we need to improve, and maybe even more important ones, which that paper focuses on. And so I don't know that this is really the right motivation for definition checking. Just kind of this kind of changed my opinion on this. I used to think this was going to be a more powerful part of the motivation. So there's a different aspect of errors, though, that definition checking does help you with. And that's that it helps you actually get the errors you need. All right, because when you're using templates without definition checking, you're never sure, really, if you've actually found all the errors of your code. You've found the errors that occur with the particular template parameters you've instantiated it with, right? And if those aren't enough, you keep writing more and more unit tests that instantiate your template in more and more different ways, trying to exhaustively test that you're not going to oh no, if I give it this weird type, suddenly I have an error message. And it's really, really frustrating, okay? It's not that the error messages themselves are bad, it's the process of even getting to an error message. If we have checked generics, it completely changes how we can develop generic code because there's zero gaps in the error messages, right? If the definition type checks, it's right? The error's going to be at the instantiation point. There's no action at a distance. There's no spooky behavior because someone somewhere gave a surprising template parameter and then 4 layers of template deep in a separate team that you haven't even met. There's a template that wasn't prepared for that, right? Definition checking really gives us a much stronger understanding of that. It enables a lot more aggressive evolution of generic code. If you want to make a change to some piece of generic code and you ship a library to users, maybe thousands of users that you haven't even met, how do you test your change? How are you sure that isn't going to break lots of users in a surprising way? And even worse, in a way that's frustrating and confusing to them. And definition checking really addresses this, right? You also don't have to write these kind of exhaustive unit tests that are, again, trying to replicate a type system through observation. Instead, we have a type system. And actually, that's, I think, the other interesting way to reason about why checked generics are kind of valuable. In fact, before we get to is static typing useful? How many folks here think that, actually, before we get to useful, how many folks here that think that static typing makes you more productive? See a show of hands. Really? How many of you are confident, certain, that static typing makes you more productive? Lots of hands.
I mean.
So Dan Liu has a really fun webpage. Sorry, this is an aside. I don't have the link in my slides. But Dan Liu has a really amazing webpage where he collects all of the research that has happened to date on this exact question. And it turns out that static typing versus dynamic typing is a topic that is researched in software engineering and computer science for which is more productive. There's a substantial body of research. The thing that you might find surprising is, at best, there is no indication that people are more productive with static typing. And at worst, the research is just garbage. And the only thing you can say is well, maybe all of the research is bad and we have no data to support any claim. Or if any of the research is good, it's about break even. Which is I don't know, who expected that result? Because I did not expect that result. Got like 2 people. So static typing, it's not clear that it actually makes people more productive. But is it useful? How many folks think it's useful? I also think it's useful. Right? Not because you're necessarily more productive, but it changes the equation. It shifts lefts when you find errors. If you want to know more about shifting left, there's a whole section in the software engineering book about this. It moves things earlier in the development process. And while that may not make you, a single developer, productive, it can make teams, especially teams at scale, dramatically more productive. It also can really help large-scale refactoring, okay? And I think this is a really good way to think about checked generics, because fundamentally, checked generics are giving you the static typing benefits for large-scale generic software. Now, I want to be clear, the large scale is load-bearing. If you don't have large-scale software, you really don't need this to get the static typing benefits. You just build all the code every time you change your template, and it's statically type-checked. You're done. But as soon as you start shipping software to users that you don't know, as soon as you start having things at scale where you can't possibly go and try every single user of your template, you lose the benefits of static type checking in a lot of ways. And we can get it back by having checked generics, okay? So this is actually, I think, a really great kind of high-level way of thinking about this. It's not the only thing. Another really great benefit of checked generics, something that Zach Lane, I think, at this conference years and years ago, tried to sit down and like get through my head. I think it took him over an hour, which I apologize for if Zach's watching this or listening, is that once you have definition checking, especially when it's complete, this unlocks different implementation strategies and even different language features like type erasure in the language. And type erasure is a big deal, especially if it's in the language. It's a powerful missing abstraction in C++. Mm-hmm. Right now we have dynamic dispatch, right, tools that just don't address our needs. Inheritance is a closed extension space. It's not open. And it creates all the compositional problems with diamond dependencies and all kinds of things. This doesn't really work well for a lot of use cases. Templates, which compose nicely, have a nice open extension space, don't provide any form of abstraction. The missing piece is type erasure, language level type erasure. And definition checking the template is exactly what you would need to achieve this. And so I think this is another kind of really compelling motivation for this. And similar to type erasure, but at a lower level, when you have these type check definitions, you can start improving just how you implement things. You don't have to repeatedly type check in every single instantiation. You've already done that. You don't have to silently generate ODR violations. You can actually understand what the implications of the templates are. And you can reduce, although not eliminate, that's a much harder thing. You can reduce how much duplicated code you have to generate. You can recognize when types are different in the type system, but fundamentally the same in terms of how you generate code and avoid duplication here. So I think there are lots of good reasons here. These are all the reasons that I think are kind of commonly discussed for wanting checked generics in the language. But there's another reason that I'd really like to talk about, because this one I haven't seen discussed as much. All right, and this is about how checked generics improve the foundations of the language. But in order to talk about this, we actually all need to understand kind of the very basics of how checked generics work. We need to understand the syntax that you use in order to write checked generic code. And then I can give you some of the examples that motivate this, and we'll walk through the foundations. To kind of explain how they work, I'm gonna hand the mic over to my colleague Josh, and he's gonna take you through that. Also, you have to pause with this because we have to do a microphone change.
Hello. Good. Okay. So what do checked generics look like in practice? So when I'm going to use the word generic a lot. When I say the word generic, I'm going to mean adding parameterization to some language construct. And that is going to encompass both the template and checked cases here. So the parameter to the generic, or generic parameter, will be known at compile time. So I'm not going to be talking about that case Chandler was talking about earlier, but with the type erasure. And this is going to be sort of the common case for high performance, relatively static languages, at least when talking about the static part of that of that language when you're using the check generics part. And generally those parameters will be types. So in some languages don't even support non-type generic parameters. Types are definitely the common case here. So what I'm going to do is I'm going to start with C++ templates and concepts, just for familiarity, and go through this running example. So with this running example, I'll show you with C++ concepts, and then later there'll be analogous constructs in a few other languages that have checked generics. So in this case, this example, it's defining a concept. The concept is called RNG concept. It requires the type that implements this concept to have a method named random that will return a type equal to a member type named result t. Of course, this is all expression validity. So this could be satisfied by having a field named random that has a callable functor type instead of being a method. So the type fancy RNG satisfies the RNG concept. And that's because it has this random method and it returns double, which matches the member type result t. Mm-hmm. So this is a generic function. The generic function can be called with any type that satisfies RNG concept. Now, calling that generic function looks like calling any other function. And that's, in this case, at least because the type parameter can be deduced from the type of the arguments. Otherwise, you have to sort of say it explicitly somehow. In C++, that would be in angle brackets. And again, this is templates. So this is where we're going to do the type checking that fancy RNG satisfies the RNG concept. And also where we're going to type check generic function with this particular instantiation with that fancy RNG type. So now switching to languages with check generics, they're mostly going to have all these same concepts. So we're going to have generic functions. They're going to have type parameters. Those type parameters will be in the signature, like the arguments and the return types. We're going to have for generic types. Very commonly, these generic types are going to have explicit type parameters, like vector int. But just like in C++, where they have class template argument deduction, there'll be languages where you can omit those type parameters in the cases where they can be deduced. Now, these type parameters will be used in method signatures in the type and the variables, members of that type, just like you'd expect from your experience in C++. The big difference that comes with check generics is that the role of constraints. So with unchecked generics, constraints are all about what the color has to provide. So in this example, the RNG concept is used as constraint on the template parameter. But this is sort of an add-on. C++ has had templates for much longer than it has had concepts. But when we talk about check generics, these constraints are essential. The type checking the body of a function absolutely depends on the constraint in order to say what are the operations you're allowed to do in the body of that function on that type. So since constraints are so important to check generics, the building blocks from constraints also play a larger role in languages with check generics. And so these are the analog of C++ 20 concepts for check generics, which Swift calls protocols, Rust calls traits, and Carbon calls interfaces. So this is a little terminology guide. I will try to use the when I'm talking about Swift, I'll use the word protocol and so on and so forth. So now there's two different approaches to interfaces here called structural and nominal. And the difference between them is how a type satisfies or conforms to the interface. For a structural interface, this means that when a type matches an interface, it's implicit. It's just because the type has the expected set of members. Now, in C++, when we're talking about concepts and templates, there's sort of an extreme form of that, which you might think of as duck typing. It's just expression validity. But there are other languages where you have structural interfaces where they actually just list methods explicitly instead of the expressions. And you still can have structural interfaces in that form. So now nominal, oh yeah?
Can I ask you to project a little bit better? I'm having
Okay.
trouble here, especially at the end of sentences to trail off a lot.
Okay.
Thank you.
So nominal is going to be explicit instead. So nominal doesn't really mean explicit. Nominal really means named. In languages with nominal interfaces, there's going to be something explicit connecting the type to the name of the interface. So this is like base classes in C++. So in a C++ class definition, you mention the base class in that declaration. Otherwise, you're not going to be able to cast a pointer between the two types, between the base class or between the descendant and the base class. Sometimes, so this explicit declaration of the connection between the type and the interface is going to look different in different languages. Sometimes it'll be part of the class declaration. Sometimes it'll be sort of separated in some way, part of a distinct implementation statement or implementation declaration. Okay, so now talk about the methods. In addition to the methods, interfaces can also contain types. So going back to our C++ example, the result T member type constraint is the analog of an associated type. So just like implementation of an interface provides method definitions defining the behavior of the type for that interface, the implementation can also provide types that appear in the signature of those methods. So think about how a C++ container will have value type and iterator member types, and those will be used in the signatures of the methods of that type, like front or begin. And in order to type check those methods, we need to have constraints on those associated types. So if you have a generic function calls begin on a container, it's going to get an iterator. But the only thing that we can do with that iterator, given that we're going to type check this function, is call methods that are defined in that constraint. That constraint on the iterator associated type. So if that constraint is a forward iterator, you can only call the methods in forward iterator in the body of that function. And unless if you want that generic function wants to do more, it has to add more constraints. So maybe it adds constraint that the element type is string or printable or some type that is printable. So this is again, checking generic code is reliant on type information that we only get from the constraints. So constraints are playing a much bigger role. So we can also parameterize interfaces. So here's another example with a C++ concept. And this is concept represent. Let's say we're raising something to a power. So we have adding a type parameter representing the parameter type of the POW method. And you can see it's here in both the concept definition and in when we use it, the concept as a constraint, we have an additional parameter there. So by parameterizing the interface, you allow a type to implement that interface multiple times, as long as it has different argument values for that parameter. So in that sense, an interface parameter is an input. And you can tell it's an input because we had to, back here, we had to pass it as an argument. We had to specify when using it. So the values of interface parameters determine which implementation might be selected. And that implementation determines the associated types. So if you have POW unsigned and POW float, they might have different result types. That doesn't quite work in the C++ examples. But in a checked generic system, some checked generic systems, this is definitely possible. Actually, there's two inputs there, two type parameters. So this is sort of a funny thing that happens with these building blocks, is that there's a first parameter that has the type that is being constrained. And now it's here explicitly written in the signature in the concept declaration. But it's not written in the. So this is called, and this is often called the self type. The self type wasn't written when we use the constraint, but in fact, in many checked generic languages, you won't even write it in the definition. In C++, it's explicit in the definition of a concept. And there's a sort of expressive power here in concepts that's beyond what you can get from a base class. It allows you to represent binary operations on a type, such as like, this method is a comparison with types of the same type. You can't do that with a base class. Or this type can be added to any type with the same self-type. So now, implementations can be parameterized as well. This ends up being very expressive. This, as an example, this could be used to implement the fallback behavior for comparisons that C++20 added, but except for it could be done in a library instead of as part of the language definition. And there'll be a lot more examples of this. Chandler will talk about this later in part 1. So now I'm going to get a little bit more about how checked generics look in actual languages that support checked generics. Now I've looked most closely at Swift, Rust, and Carbon. So I'm going to show you what it looks like in those. So now, remember my running example, I'm using C++20 concepts. This is a C++ concept definition. Now, C++ generics are structural. So there's nothing in a type definition that says anything about it satisfying that particular concept. It's not named. The only thing is that it implements the random method that's expected by the concept. And this is in contrast to the sort of more explicit statement that it inherits from the base class. So this is a definition of a generic function. Again, the name of the concept is used in a constraint. And this is what callers have to satisfy. And there's a type parameter, t here. And it can be deduced from the function argument. So now I'm going to talk about Swift. So Swift would be my first example of a language with actual checked generics. And again, these are called in Swift, interfaces are called protocols. You can see an example here. It has an associated type, in this case called result. It also has a method. This is a mutating method. But notice how the method declaration here actually looks like a method declaration in a class or a struct or whatever. And that's really because this is about the type system rather than expression validity. This is the common pattern you'd expect to see in checked generics. So protocols are nominal. So they're listed explicitly in the class definition. And they're listed, in fact, together with the base class. Though this is actually listed as a regret by Swift designer Jordan Rose, who would prefer maybe something a little more to distinguish these two different things. But this works fine. So in order to conform to this protocol, we have to implement the random function. And the implementation in Swift is not separate. This is an example where you just implement the methods in the class, and that's all you need to and state that you satisfy this protocol, and that's enough. Now you see, as part of type checking, that Swift is going to look and say, oh, we need this random function, and says, oh yes, it does have this random function. When it's part of that, it's going to notice that the associated type is going to have to be double. And so you don't say this explicitly in Swift, it's just inferred. So now here we have a generic function, with the type parameters before, and a constraint. They're listed in angle brackets. And again, this is checked generics. So this constraint is going to be used to fully type check the body of this function definition without even knowing what to use. And this is what using an associated type from the protocol looks like. And here it's used for the return type. So there's some things that Swift does not yet do. Check generic variatics are a work in progress. I think this is actually going to land really soon. There's a lot of active work on that. But beyond that, there's a number of features of sometimes present in other languages that are not present in Swift, including specialization. And I should mention that the term specialization actually means a couple different things in different languages. Here I'm meaning specialization in the sense of like C++ partial specialization. There's no parameterization of protocols, no overlapping conformances, no non-type generic parameters. And I actually believe these omissions are intentional. I don't think, like for example, parameterization of protocols is very useful if you're maybe doing operator overloading using generics. Swift doesn't use generics for operator overloading. It has some other mechanism. And so it's just a lot simpler to not have that feature. And overall, there's a sort of a very strong focus on Swift on usability, and the additional expressiveness that maybe these features could add are just not going to pull their weight in Swift. So really there are a lot of choices here in the design space. I'm not saying this choice is bad. In fact, this choice is probably the right choice for Swift. So now, in comparison, we'll look at Rust. So Rust interfaces are called traits. So remember all this different terminology. This is a trait definition. This is an associated type declaration. And this is a mutating method. So traits are nominal. So we're going to have an explicit declaration that the trait is associated with this type, is implemented for this type. Implementations of traits are separate, unlike Swift, from the type. and in fact, just appears totally outside the struct definition. So the way it works in Rust is even though it's not appearing in the definition of the type, all the methods that are implemented in traits are actually end up part of the types API. So random here ends up being a method that you can call on a fancy RNG. Here's a generic function where we actually are calling that function, that method, the random method. We again have a generic type parameter declaration using angle brackets and returning an associated type. So Rust has a much greater focus on having an expressive generic system. And as part of that has recently added some more advanced features. So generic associated types, so again, generic means parameterized. So this means you have a parameterized associated type. This is a bit like when you have a C++ member type that is itself parameterized like a templated member. It also has non-type parameters, which in Rust are called const generics, just like the non-type parameters in C++, C++ templates. And both of these features have been shipped in stable Rust. They're still in a maybe a little bit of an early form, and there's an expectation that they will continue to be developed further. There are some things that Rust doesn't do. So we talked about Swift doing Variatics. Rust does not expect to have generic Variatics anytime soon. And there's there's been an ongoing interest in adding specialization to Rust, but it's been hard to do because of the legacy. And this is something I'm going to talk about in much greater detail in part 2. Lastly, I want to show you how this looks in Carbon. So I'm going to go a little bit more detail here because Carbon is my thing and also probably the least familiar to all of you. Also probably changing the most. So this is an interface definition. We actually call interfaces in Carbon. An associated type definition and a declaration and a mutating method. So now we're going to talk about how we say that a type implements an interface. So again, interfaces are nominal in Carbon. So there is a separate impl definition but in Carbon, unlike Rust, it can actually appear inside the class. We have this thing where we only do name lookup into things that are mentioned in the class definition. If you're going to have to look at some other entity to find names, we use the extend keyword on something in the class definition. So this means by using the extend keyword is used with inheritance because when you inherit from a base class, you're going to want to look at the names from the base class. And it's optional for interfaces. So in this case, we're using the extend keyword with the interface. And so that means that random will be part of the class's interface. If we didn't use extend, then it wouldn't pollute the class's interface. So here's a generic function. Type parameters in Carbon are either always deduced, and when they're deduced, we put them in the square brackets here, like the angle brackets in other languages. But if the type parameter was never deduced, we'd actually would put it in the round parens. So it's the position being in the square brackets and round parens is not actually how we decide whether it's a generic parameter or not. It's whether it's deduced or not. If you see that colon exclamation point, the colon exclamation point is actually the thing in carbon that marks the parameter as being a compiled time generic parameter. Again, here, the interface's result associated type is being used as a return type. So probably the biggest generics feature that distinguishes carbon is the fact that it supports both checked and template generics. So the checked generics use the nominal interfaces, just as I was showing in that last example. But template generics work a lot like C++ templates. They directly instantiate the type. They maybe constrain in a way much like C++ 20 concepts. I know there was a question in Chandler's keynote yesterday about this. This is really a big topic. But that is part of the story here of how Carbon is going to have very good interop and migratability from C++. And checked generics and template generics can call each other and in either direction. We do support interface implementation specialization. We're doing that from the start. Again, more on specialization in part 2. We're also supporting checked generic variatics. Of course, when I say the word supporting, Carbon is very new, very new. And all of this is a work in progress. But we think that by learning from other languages, we can build an even better generic system, really advancing the state of the art here. And I would now like to give you Chandler back.
Really awesome. Thank you so much. All right, folks, still feeling good? See, Marshall actually understood. He took my advice. All right.
Sitting still is one of my worst things.
So, I am with Marshall here. Standing up is good. Moving around is good. And so let's move around. Well, let's move around and talk about something that I was not really expecting checked generics to provide when we started working on this. I really didn't see this interesting thing that we could build kind of categorically better language foundations with our checked generics. So I want to kind of showcase how that is. And as part of that, we're also going to use a bunch of examples because I'm trying to show how checked generics kind of can impact the foundations of a language. I'm going to be using a lot more Carbon examples because we've had the opportunity to kind of explore this space very directly. But the point isn't really about Carbon. The point is about what this does to change how the language even works. And so the first thing I want to talk about are the kind of having unified and powerful customization points. And I don't know if everyone is kind of familiar with the term customization point, the way it's used in C++. So customization points, if you have some class, myComplex, and you want to customize how operator plus works, you can overload a function there. And in C++, you can do this for things outside of operators. You can do this for the swap implementation, and you do that by overloading a swap function. But these aren't just normal overloads. These are overloads in the same namespace as your type. They're found through argument-dependent lookup. And so they allow you to customize behavior from other pieces of code calling it. So if you go down into some code and you call std_accumulate, which is a template, std_accumulate internally is calling operator plus, and it's actually going to find your definition because of how ADL works and how all the name resolution works. And this allows you to customize how std_accumulate behaves. It's the name's customization point. And if you call partial sort, this is going to customize how swap behaves inside of partial sort. And this kind of emerged from argument-dependent lookup for operator overloading when C++ was originally being designed. And then it kind of became a thing where we wanted to use it in a lot more different places. And ADL and the operator overloading model didn't always work well in all of the other places, and so there's been a long, long history of trying to find different tools to allow people to customize behavior. You have class template specializations for your type, but that requires you to reopen other people's namespaces, which is really bad and frustrating. You have ADL found functions with a weird little using trick, which is pretty common, but it's easy to get wrong. It has some limitations, and it means that just calling functions, unqualified functions in C++, often has very surprising effects. And so then there was a further iteration towards customization point objects, or CPOs. And those ended up having some limitation, and so now there was work on tag invoke, and then there's a paper that's trying to improve on tag invoke. The history here is really monolithic. There's a ton of papers in the committee about this, but P 2279 has a nice overview. All of this history is there, as well as all the details about what went wrong, what we're trying to do to improve things. And the interesting thing for me is that when we looked at checked generics, we ended up building a lot of infrastructure. And it turns out that some of that infrastructure addresses this problem. So specifically, when Josh was introducing checked generics, he mentioned how constraints are much more important in checked generics. And so we have special language tools to model constraints, interfaces or traits or protocols that let you model these. And this extra infrastructure that we built for checked generics also allows you to do really powerful customization. And so let's look at some examples of how we can reuse this infrastructure for this powerful constraint infrastructure, not for a constraint at all, but just to kind of do customization. So here's an interface in Carbon, right? And this is an interface that's going to allow us to customize the operator behavior of multiply or star, right? And the interface name is mulWith, because we're going to multiply with something else, some U-typed object, right? So this is also a heterogeneous customization point. We have our associated type for the result of that multiplication. And we actually can provide a default. Most types are probably going to actually return their own type as the result of whatever multiplication. And we have a function op, and in Carbon, kind of a convention when we have a customization point that only has one meaningful function in it is that the interface name is the important name, and the function name is just op, because we don't need to say multiply again here. And this is a method that takes a self parameter and a right-hand side and does the multiplication and returns the result, right? And if you want to customize how multiply works, how would we do that? So we have a class point, and we want in point to support multiplying with a floating point number, right? So you can take a point and you can multiply it by some floating point number. And so we implement that interface, and we say that the result is going to be point. Okay, so this is going to allow us to do a multiplication with a floating point number and give you a new point back. And then we implement the op function with the implementation of this, and we're just going to scale our point. Right? And once we've implemented this, we can reuse all of the generics infrastructure for having this interface, having an implementation, finding a particular implementation for a particular type of an interface to actually customize how operator star works. So down here in my function, I write p star scale. And in Carbon, this is going to basically be rewritten to this qualified method call, okay? And this is just a way that we can explicitly call not a method directly on a type, but a method of some interface that that type implements. Well, there's a tricky part here. We don't yet know which interface. Sure, it's some multiply, but this is a generic interface, right? And it can implement it for many different things. We actually have to extract the type of the right-hand side. We use that as the parameter to the generic interface. And so we're actually looking for mulWith f64. We get its op method, and then we call that method with the scale. And this does kind of the customized operator star. So there's a whole lot of syntax. Just want to make sure. Yes, Marshall.
I'm missing a bit here. How you go from the star to mulWith.
So the rewrite from star to mulWith is the definition of star in Carbon. The compiler just does this for you. This is how it implements star.
Okay, so you have an add with and a div with.
We have an add with, we have a div with, we
How
have
with.
all of these interfaces. This is, instead of having an operator plus function that you can overload,
Okay.
we have an interface that has a special name that we use to implement each operator.
Okay, thank you.
Yeah, great question. P, scale, yeah, okay. The other interesting thing here is that this is a deduced return type. And so we actually need to know the type of P times scale in order to compute this auto. I'm sorry, a question, Zach?
Yeah, so I thought the colon bang meant deduction, and you've got this default of the result type to be self. So why do you have to say where dot result equals point? Why isn't that deduced?
Okay, just let me make sure. So the question here is about this colon bang and result.
Yeah.
Okay, so the
other colon
bang.
with you,
I'm sorry.
and the other colon bang with you.
The other colon bang with you. Okay, so the colon bang means that this is a generic parameter in U. It doesn't mean that this is deduced. Right? The squares are for deduced. The colon bang means it's generic.
All right, thanks.
And when it's not in a parameter, the colon bang has a similar meaning. It means this is a compile time thing. It's not something you can, like, it's not a runtime type. It's a type, right?
This other point is probably true.
I'm sorry?
The other point that you probably didn't have to say the where explicitly because it doesn't default to the string.
I didn't have to say the where explicitly. Oh, yeah, sorry. This where is also completely redundant. It's just for illustration of how you would do this.
Are there ways to implement mul with that are more symmetrical as opposed to p dot mul with? You just have mul with two parameters.
So the question is there a way to implement mul with that's more symmetrical? That is a really great question. I would encourage you to ask that at the end when I can pull the other presenters up to answer that question because it's going to be longer than I can manage. I'll get it wrong. They'll have to correct me. John.
Procedural question. When you say the end, do you mean the end of this session?
The end of this session.
Okay.
Sure.
Not the end of the entire.
No. Yes.
So just to clarify, that section on line 10 is redundant because of line 11? Or?
Because of line 2, where we have equals self.
Right, you're specifying something that's been defaulted to the same.
So we have a default that's already there, and that default would be the same as what we're specifying.
Oh, I see. It's in
Yeah.
the class point. I missed that.
Mm-hmm.
So we tried to show too many things on one slide. Yes.
This all makes sense to me now. How would you write scale times p?
That is an even better question to ask at the end of this talk because so we have a whole. No, I can answer this one. So this is a great question. How do you reverse these things? So this is an immediate question we have. We have a whole set of language features to specifically allow you to easily implement symmetric interfaces.
So
we
when
don't
your
have any
operation
examples
is
of them.
commutative, say,
Make it from Python.
The simple answer is you can write impl f64 as mul with point.
okay, thank you.
Yeah, sorry, yeah. So you can reverse this, and then we have language features to do it automatically for you. Okay. So the other thing I wanted to mention is that we do use this result type to figure out what auto is, and we get it from that where clause. It's mentioned like that's redundant. If we didn't have the where clause, we would get it from this default at the top. All right, folks, fairly happy with this? So this is maybe the least surprising of the customization points. Let's look at some more interesting things. So once we're not using a single operator overload, like operator asterisk, to do the customization here, when we're using an interface with a name and with different members, we can start doing something really nice. We can have higher level semantics associated with your customization point. So we can have a choice. A choice is like an enum in Carbon, ordering, and so these are just different options: less, equivalent, greater, and incomparable. And then we can have interface ordered with. Again, this is a generic interface, right? It takes some other typed, and we have a single function here, compare, which says we're going to compare ourselves with this other object. We're going to return one of these choices, like one of these, enumerated states, to tell you where this is, right? This is basically like spaceship in C++. And in Carbon, when we're actually implementing overloads, I'm sorry, there's a hand. Did I miss it? Thank you.
No, I just wanted to ask about the previous topic. So if you define the symmetric operator for two types, you get similar problems that you get for ADL for C++, right? Because now you need to resolve which one. So.
All right. So the question is, if we end up having two different implementations that are symmetric for two types, can we end up having some of the same confusions of ADL about which one do we find and when? That is a risk. That's a really important risk. And there is an entire section of part 2 to address that risk because it's so important. This is actually a super, super important thing that we have to solve for generics anyways. And what we end up doing with the symmetric operators is we just end up benefiting from that solution. And so we've had to give a good answer for this in terms of generics anyways, and the operators then benefit from that. So this is a great question. It's a great observation. All right, so we have our spaceship-y like compare here. And then when we're implementing multiple different operators in Carbon, we can lower them to different kinds of things. So we can actually call the same compare function on an interface, both for less than and for greater than. But then for the less than, we can check that it's less. For the greater than, we check that it's greater. And we can get kind of spaceship-like behavior. And one of the really nice things for me is that with operator spaceship, we had to add a lot of machinery to the language, and machinery that was visible to type authors, right? Like the type authors have to be aware of how spaceship and all of the other operators kind of interact.
So Carbon implements the spaceship operators with ordered width.
I'm sorry.
Does Carbon implement the spaceship operators with ordered width, and then you override that interface?
So the question is, does Carbon implement the spaceship operator? No, I'm just drawing an analogy right now. Okay. So in C++, the spaceship operator, when we added it, we had to add a lot of mechanics to the language that type authors had to be aware of in order to overload and actually implement this. And with Carbon, the mechanics we're already using with interfaces have the expressive power to let us talk about things that are more semantic and at a higher level. Right? They don't have to precisely model the binary operator that we use for less than and for greater than. Carbon doesn't currently have, to go back to the question, Carbon doesn't currently have kind of operator syntax for spaceship. I don't know if we're planning on adding it. I guess we could. But because we didn't need a special symbol or a special operator for types to customize, because we can do something like ordered with the compare function, well, we didn't need to add that, and I'm not sure if we would. You could always just call compare as a function. Question?
I hope this isn't off topic. Are the names less and greater here available unqualified in Carbon?
No, it's just slide code.
Oh, okay.
Sorry.
Okay,
It's just slide code. Sorry, if I add all the qualifiers, it just gets really, really, really big. Okay. Also, I mean, it's not the only thing that's slide code about this. Like Carbon's actual customization of less and greater is quite a bit more complicated. There's a whole lot of other considerations if you want to have really rich customization here, especially once you factor in C++ interop. There's a whole bunch of stuff that we're doing there. But this is the kind of high level thing. And in particular, this is roughly what type authors have to interact with very often. We can do more interesting things here. We can also incrementally extend and specialize our customization points in a way that's kind of very, very easy to do, and it's also not a breaking change. So if we started with this ordered with compare, and maybe we shipped that in some version of the language, and years go by, lots of people implement it, that's wonderful, it's great, and someone complains to us that, like, look, it's nice that we have this through a comparison thing, but their type would actually much prefer to specialize a few of these operations and just say, like, no, for less, I know what I want to do. We can actually introduce more methods to this interface in a way that is not a breaking change. And because we have a whole interface, because we have this larger piece of infrastructure, this is pretty straightforward to imagine. So we have extra functions that we add to our interface, like less. But we don't just add it as a function that is required. We also mark that we have a default for this function. That means that this function does have to be present, but if the type doesn't provide it, the interface already has a default available, right? And the default, of course, has to be implemented, and in the implementation, we simply implement this in terms of the original method. And so this both gives you kind of smooth extension without breaking changes. It also gives you a really powerful way to customize behavior and have a pretty rich set of customized behaviors directly in the kind of interface stuff. And this is a pretty powerful kind of customization point at this level. All right. Let's talk about even more interesting customization points. So another thing that generics let us do, because we're reusing these building blocks that were kind of in the language designed around checked generics, it turns out they work really well with generics. And so if we want to have a generic customization point, all of the pieces already work for this. So you can imagine we have some printable interface. It's got a print function, not too surprising. And we could also imagine some vector type. Maybe it's even a template vector type. It doesn't have to be checked generic. It can work with checked or template generics. We now want to implement printable. But we don't want to implement printable for all vectors. We want to implement it for all the vectors that we can. It's going to be a generic implementation, though, and so we use a for all keyword to kind of signify that this implementation is actually over some set of types. Okay? And so we're going to actually have a binding T for which type we're implementing this over. And the set is constrained. It's constrained with our interface printable. And so this is an implementation for all the T's that are printable. And for those T's, you have vector T as printable, and you have the implementation. And the nice thing here is not only does this say which types does this implementation apply to, it's generic. And so it also makes the body of this implementation have T as a generic type with, and so when we use T, we can use print on it. Right? So we both get the constraint to do the conditional implementation in the places where it applies. And at the same time, we get the ability to write definition-checked, type-checked version of the code because the constraint and the definition checking are all tied together. Make some sense? Okay, so we have more powerful customization points. How do we embed these even deeper into the fundamentals and the foundations of the language? Well, here's a really frustrating part of C++, implicit conversions. Right? Maybe we can actually have a more uniform way of handling implicit conversions. Actually, scratch that. Maybe we can have a more uniform way of handling all conversions between types by reusing the more powerful customization point tool. So we can have explicit conversions by having an interface as, and this is, of course, going to have a parameter type destination, like what type are we converting to? And we have a function that converts from self, right, the type implementing this, to the destination, right? And now when you want to say that something is convertible, you implement string as path. And this says that string is going to be convertible to path. And you can implement that conversion using custom code because we know how to do this, right? Path.from string, some code in there. And now we have a binary operator to do conversions, right? And so this little binary as operator works similar to operator star. Right, we're going to take the left-hand side, we're going to call a qualified method on it, we're going to go find the as path interface, and we're going to call the convert method there. Make some sense? Yes?
Can you synthesize some of these conversions? Like if you knew you had the from.
Hang on to that one. I've got a slide for that. So we don't just do this for explicit conversions, we can also do this for implicit conversions. And we can even model the relationship. So we have an implicit as interface that handles implicit conversions. And this interface extends the explicit conversion interface. Right? Because you can't be implicitly convertible without being explicitly convertible. You never want that to happen. That would be very, very broken. We can actually represent that directly in the constraints. It doesn't have to be kind of a language rule that comes out of nothing in the standard. It's actually written in the code. And because we're extending as, this means that there's a convert function here available. We don't need two versions of the convert function. And now we can say that maybe string is implicitly convertible to string view. This will also, of course, mean that string is convertible to string view, but it's an implicit conversion. And now when we come down and we call some Greek function that accepts a string view parameter, we pass it a string parameter. Carbon can look at this, and to implement implicit conversions, what it does is it actually just calls implicit as, gives it the type that it's trying to reach, string view, right? Finds a convert function and calls that convert function. Okay, and so the same set of building blocks can build implicit and explicit conversion. And we don't have to just wait for the types to provide these. We can actually provide these automatically, as someone was mentioning. So again, these building blocks all came from generics, so they all work well with generics. We can use that to build conditional default implementations. So you can build a generic implementation for all of the U types. This one's unconstrained, so it's literally all of the U types and all of the T types, but where T is convertible to U because it implements as U. Okay? And when that's true, we also want optional T to be convertible to optional U. So now all those conversions just work, and in the body of this routine, like when you go to implement this, right, you have T as U, you're going to have the generic constraints you need to actually implement this as well. We can do this for explicit conversions, we can do this for implicit conversions, we can even do this for things that are a little bit weirder. So for example, here is an implementation for all T's, unconstrained. But for a single type, null opt, so there's one type null opt, which we allow to implicitly convert to any optional T. Right? Okay, and now a bunch of hands go up.
So the two implementations you have on line 1 and 4, right? If I just had 4, I would get 1 for free because implicit as extends as.
Yes.
If I had them both, is that a problem? Would it like?
What does my compiler say?
So it's only ever going to use one of these. If you use the word as, you're going to use the first one. If it's trying to do implicit conversion, it's going to use the second one.
I don't believe my compiler yet. I think this is an error, but I don't know. We should put this into the Explorer. This is on the slide for illustration. But yeah, this might actually be an error because you've already done an as and then you do an implicit as. Ball.
So, in a way, the implicit conversion is kind of a global understanding that we have on our type system. And if you have a library that defines implicit conversion in a way string to whatever, and you have your own code defining implicit conversion from string to something else, could that too, could that collapse in your original logic?
Yeah, so the question is, right, like, from which side does the implicit conversion come at? This is actually the same question as the question about the symmetric operators, it turns out, I think. Well, hold on, and I think that it will also be answered in the section in part 2. Okay, jumping back to the previous question, I think folks have had more time to consult.
I think there is a redundancy here, and it will be resolved by the explicit statement about which is prior to, because they are happening in the same way.
Okay, these are allowed, and it's actually going to be resolved by like the one that comes first, something like that.
The one that comes first in the spelling in the source.
Yes. John.
Do you actually have the ability to declare that T is convertible to T this way for all T, or is that magic in the compiler?
Do I have the ability to declare that T is convertible to what?
T itself.
Itself. I'm going to let Richard.
Yes, you can, and that info is in the prelude.
Okay.
Like, so Carbon just provides that automatically.
It's not magic, though. It is.
No magic needed. We're running a little low on time, but I'll try and take a couple more.
Okay, there's one thing that's implicit here that is implied by all this, and that is that users of types that you define in a library can define conversions, define implicit conversions that the library authors did not provide.
Not quite.
Okay.
A little bit. Again, part 2 is going to directly speak about. We have a whole section about who gets to provide these impulses.
Okay.
It's a really important question. Okay, but I want to talk about a few other things we get to do with this customization tool. So this is some C++ code, just to be clear. We're switching back to C++ briefly. So this is some code that works. We have a base class, the derived class. We have a function that accepts a pointer to the base class, right? We make an object B, we make an object D, pretty unsurprising. We use a ternary operator to select between the address of B and the address of D. Now, I always want this code to compile because it's really obvious how to do this, right? There's a base class, and we should just send the base class pointer along. That's how inheritance is supposed to work. And this does work in C++, which is great. And I mean, it even works if we swap the order around, which is good. Well, what about this code? So we have derived A and we have derived B. We have two derived classes, right? We have the same test, right? But we build the two derived classes. We build objects DA and DB. And then we try and actually select between either the address of DA or the address of DB. And I feel like this should work, right? Like we still have a base class. We know what the type is that we have to be using here. This seems so straightforward, but C++ will not compile this. Because it's like, I don't know how we could possibly map from derived A and derived B to this. And I mean, this is the inheritance example, which for me is in some ways the most frustrating, but this also comes up with library types. Think about things that could be string views, but are not currently. Maybe you have a string and a string literal, or you have two different string literals, or you have an intern string. There's so many ways that you get to this, and there's no way to really fix it in the language. A little bit low on time, but a quick question for Marshall.
Is this specific to the ternary operator?
Yes, this is very specific to the ternary operator. This is about ternary.
Okay.
There's not something else going wrong here. This is the ternary operator.
I just want to add very briefly that it's also the value category, not just the type. It's kind of
There's another problem with ternary around value category as well. But I'm talking about the type problem. But we can actually make this really easy in Carbon because we can build, we've built this kind of customization system on top of the generics building blocks. So we can actually have an interface common type with, right, some type. Now this is something that is really hard, not quite impossible, but really hard to even contemplate with customization points in C++. This is actually a customization point entirely on types, not on values. There's no function in here. All we have is an associated type. This is a way to customize just the type system. All right? And so the result type of this common type with is going to have some also really important constraints. We require that whatever the common type is, the type implementing common type with can be implicitly converted to that common type result. And we require that whatever the other type is, can be implicitly converted to the result. Okay? Dot self here refers to result. Self here refers to the implementer of common type with. I know it's a little confusing. We haven't found a better way to spell this yet, but they're two different things. So now we have our intern string type. Our intern string, of course, has a common type with string. Of course, it should have a common type with string, and it's pretty easy to see what that result type would be. It would be string view, because intern string should be implicitly convertible to string view. String is implicitly convertible to string view. And this solves our problem. We can solve it because this is in the library. We can solve this for any library types that need this, right? We can actually select between S and I, where S is a string, and I is an intern string, and we know what type to pick here. The type you pick has to be string view. Make sense? We can even have this string view, we can have this be a deduced type because there's no need for extra type information. Common type with actually directs us to the right type right out of the gate. Because we have common type, we can keep going making the foundations better. For example, if we have a deduced return type of a function, and we have not just one return statement with the type of string, but a second return statement with a different type of intern string, and then a third return statement with the type of string view, we can chain common type with together to find the common type across all of these returns. That's what we want to deduce for auto, and now we know how to implement all these returns. And so it makes lots of parts of the language a lot more robust and rigorous because we have this foundation that's built on top of the generics building blocks. So my whole thesis here is that checked generics build better programming language foundations. When you use the checked generics infrastructure to build your entire programming language foundations, you get really powerful and compelling foundations for the language. But there's a second point that is really interesting here. Once you do this, those better foundations actually make generics better in the language. Okay? Because every time you go and you build your foundations of your language with checked generics, they become available within the checked generics, and not like available with some kind of new language feature that you have to bring out of whole cloth. They're available by construction, right? We had operator overloads from before, just the same operator overloads as before. Without any new infrastructure, we can already use operator star in a generic function, right? In our generic double, we require T to implement molewith F64. And now we can take some X of type T, and you can do X times scale, and we know that this is allowed because we required it in our generic. We even know how to implement it because we lower this to molewith F64, right? We have that in the constraint. We even know how to resolve the auto return type because we have the return type in the interface, which is an associated type of that constraint. And so the implementation has to be providing us with the correct return type here, right? We didn't add any infrastructure to the language, and we got operator overloading to work perfectly inside of generics, right? The same pattern lets you do generic implicit conversions, common type within generics. All the language foundations that are built on top of the generics infrastructure are suddenly readily used in generic code, right? And so when we start doing this systematically, right, when we systematically have these generic language foundations, we get to ensure that generic code is just code in that language, which is really like the banner feature of generic code. I can't tell you how many times I've been in committee talking about generic code in C++, and they're like, our goal is that generic code is just code. There's no difference when you're writing it generically or normally. And the best way to get there is to look at the building blocks of your generic system and then rebuild the foundations of the language on top of it. All right, so really briefly, some concluding thoughts here, right? Generic programming is better with checking, ergonomics, more available ergonomics, right? You get the powerful abstraction tools like type erasure, get efficient implementation strategies. And the entire language benefits from this as well, right? You get better customization points. The language constructs are much easier to customize. You have clean interface composition. You have good extensibility here. The generic programming becomes simpler as the language foundations are always integrated with the generic system, right? There's no difference between non-generic and generic code. And this is an area we're trying to explore with Carbon. Like, what would it look like if we took this to the fullest extent, right? And then what does it look like if we even import things like templates, how to do specialization, can we pervasively integrate this? And our hope here is to just share, like, this is the experience we've had, this is why it's so impactful. We'd love to work with anyone who wants to kind of follow up in the space, whether it's on Carbon or C++ or other places. I think this is a really, really important thing for programming languages in general. Also, I do want to mention we do have a part 2 after the break. Really encourage you to come here. Richard and Josh are going to walk you through the really hard parts of checked generics. This stuff often goes over my head. It's so much fun. I'm going to be here. It's going to be a blast. And with that, thank you so much, and I'm happy to take any questions about part 1. Any questions left? There was a question we deferred, so we should at least get that.
Yeah, can you talk about the symmetric operators?
Can we talk about the symmetric operators? I actually think you want to stay down there where the microphone can hit you.
Okay. So we can have an info for all that says by default, if you implement it one direction, you get the other. The other thing you can do is you can explicitly say both ways. And what ends up happening is that there's only one place that can define any of these because of the dependency relationship says that only one of those libraries will have both names.
So just let me see if I make sure I got this. So there's dependencies and other things to make sure that only one place actually has the definitions. You can explicitly provide kind of both directionalities if you want, but there's also a default tool that makes things symmetric if you don't provide it yourself.
Right, but that has lower priority.
But it has low priority, so if you provide it yourself, it always wins. At the back.
Does the impl for all types that satisfy X interface, does that require knowing the set of all possible types that at like compile time, or is that capable of supporting like if that definition of the impl for all is like used by like an external library or something?
No, totally understand. Like while it is a set of types, right? It's not a set of types we enumerate in any way, right?
Okay.
What it means is that this impl will apply for all. In some ways, it's almost for any. And we do it like as we find types and we need to find an implementation of an interface, this is one that can satisfy it.
And can you clarify how that is different from asserting satisfaction on template instantiation? How is this different?
I mean, there's some subtle differences, but it's not different at like the big picture level. It's the same kind of idea, but for nominal interfaces. That's probably the biggest difference, is that, right, you have this mechanism with templates, but not for interfaces. There's not this interface component here, but it's a very similar idea that you would have for templates.
Okay.
I'll come back. I'm just trying to get other questions over here.
Probably getting ahead of myself, but this is sounding very similar to the orphan rule.
Yes, this is sounding very similar to the orphan rule. Part 2 has a great section to talk about that.
That's what I thought your answer would be.
Sorry if I missed this, but can you implement interface for another class? Like,
the question is, can you implement an interface for another class? Notionally, yes, you can do this. But there are restrictions around who can do this, where, and how that works, because we don't want anyone to be able to implement any interfaces anywhere. And a lot of the subtleties of those restrictions are what lead to one of the topics in part 2.
Sorry, in terms of operators, I was more wondering, like, to use C++ terminology, like a member function operator versus a free function operator.
So your question is whether there's a member function operator. For operators, there's not really a member function approach. But if you have a member function that you want to use for your operator, you can like alias them, but they don't work as member functions.
Sorry, no, I meant like where here you had p dot mul with something versus if you were to have mul with 2 arguments.
I'm just going to get the example.
Are those both possible in part?
Oh, okay. So you're asking, could we, instead of rewriting it this way, could we move p over here somehow?
Yeah. So mul with had like 2 type parameters and 2 arguments instead of.
I actually advocated for doing this, and it didn't work out well. And I don't remember all the details about why. But my vague memory is that it didn't actually simplify any of the symmetric things you would kind of hope that it simplifies, because you still have to pick which order they go in. And not doing that allows it to reuse the existing generics building blocks much more directly. And if you're not getting any benefit from that, we might as well just directly reuse the existing building blocks rather than adding special machinery to find generics when you're not calling methods.
Okay, so that's not possible in Target.
No.
Okay, thanks.
Yes, a question on that slide. It seems that you mandate that the result type is either the left-hand side argument or the right-hand side argument. If you wanted to implement something like physical units, you multiply meters with seconds, and you end up with a completely unrelated type. Would that work?
Yeah, so that's why we left this, even though this is redundant, we left this in the slides, because you can customize the result type to be any type you want. The one at the top is just a default. At the back.
So I don't remember seeing a case of a type constrained by 2 interfaces. So what I'm wondering is, how do you build something like arithmetic where it's like mul with
And something else.
div with, et cetera, et cetera?
You literally write mul with ampersand add with. We have a whole set of operations to compose interfaces and constraints.
Okay.
And we also have a mechanism to give names to those kind of combinations.
Yeah,
I'm sorry.
you can give names to the combinations as well.
Okay.
I think that's all in our time. Thank you so much, and hope to see you at part 2 in half an hour.